zero. Sure, because as you approach zero from the positive side goes to plus infinity, approach x through negative values, you go to minus infinity. So the function itself is not even defined at x equal to zero. Okay? So what I can say over here basically is f of x is defined for all x not equal to zero. So just one point where it's not defined. Okay, now let's go to the differential equation and look at this. Okay? What happens is that when I talk about the differential equation having a solution, okay, implicitly in that definition, okay, or I made it explicit, the derivative has to exist. Otherwise, it doesn't make any sense, right? Now I'm talking about solution of differential equation, and unlike the function 1 over x, okay, I'm also requiring that the derivative exists everywhere, okay? Well, we get the problems over here at x equal to 0, okay? Now, to make this a little more concrete, let's look at this thing and give us what's called the initial value problem. I'm going to give you now a requirement that the differential equation not only be satisfied, okay, but also has to go through a certain point. Okay, let's do that. So now the problem is solve dy dx equals, well, let me put it in the original form, same equation, xy prime plus y is equal to 0. And also I want the curve to go through x equals 1, y equals 1. Okay? Well, will 1 over x work? It's a solution. 1 over x is certainly a solution to the differential equation, right? And basically 1, 1 lies on the curve. Now what I want to show you is the following. Okay? X versus 1. Okay? Let's just look at the top, that first bracket thing over here, right? That contains the point 1, 1, right? No, why didn't I draw the curve over there? Because the point 1, 1 doesn't lie on that curve. You see? What we're requiring now for a differential equation is not only should the equation be satisfied, which is true for this arc and this arc, but it has to go through a certain point. Okay? So if we're required to go through 1, 1, okay, that basically says that the solution of the differential equation is limited over there, right? I can't take any branch over here, right? Because there's no point on that curve that goes through 1, 1. So what happens is that once we give an initial condition, it kind of removes the ambiguity, am I on this branch or this branch? It tells me I have to be, in this case, on that branch. Okay. Let me just talk about this again. It's a simple problem, but imagine a much more difficult one. Okay, here we can solve that analytically and everything. Suppose that we were really, crazy, and I said, okay, I'm going to solve this equation using MATLAB. Okay, you can do it. Okay, even though it's so simple. So you code it up, and we'll do that later on. And you say, solve this differential equation, go through 1, 1. And of course, what will happen now is you have to tell MATLAB, do you want to march to the right or to the left? Right? MATLAB can go either to the right or to the left. You go to the right, you'll find, okay, 1, 1, and then you'll find 2 1/2, you'll find 10 1/10, and you'll see asymptote. And if you graphed it from 1, 1 on, you pick up this graph perfectly. Okay? Now suppose you said, let's march, tell MATLAB to march it to the left. Okay? So you go here, here, you go to 0.01, this is 100, right? It's reflecting the fact that there's a vertical asymptote over here. Okay? And if you ask MATLAB to go to x equal to 0, it would blow up, right? No surprises, we know what the solution is. Imagine the following. Suppose I had a much more complicated equation that I wasn't able to solve analytically. Okay, and I do the same thing. Let's just suppose, for argument's sake, that this is a much more complicated equation, but the graph looks something like this. Okay? And then I have no idea a priori what the solution looks like. I tell MATLAB, march me to the left, and what's going to happen? If I'm not cognizant of the fact that something weird happens x equal to 0, it'll blow up. Okay? And then you'll say, gee, what's wrong with MATLAB? And then you go through the documentation, and you'll spend hours and hours, changing the tolerance, the precision level. There's just a gazillion things you can adjust in MATLAB, and you'll never succeed in getting the solution. You get very frustrated. Okay? But probably that equation came from some physical problem, maybe even something with a shock wave, like I said, okay, or some other type of thing with the boundary layer. Okay? And that that's basically the mathematics reflects the physics if it's a good model, okay? So knowing things like this are very important. Like I said, I illustrated with a trivial problem. Say, gee, I could have told you that right away, but I can give you an equally complicated, I can give you a much more complicated equation, okay, that has this behavior, and there's no way, a priori, that you would think that anything can happen is bad at x equal to 0. So you always, when you have these models, okay, and there's certain, it's called singularities, for lack of a better term, you always have to keep those in mind, because if the model is good, the math model is good, it's going to be reflected in the numerics. So, to sum up over here, the function 1 over x is defined for all values of x not equal to 0. Once I tell you an initial value problem like this that goes to 1, 1, what's the domain now in the solution? See? Over here, I'm talking about the domain of 1 over x just as a function. Nothing to do with differential equation. Now, when I look at the solution of the differential equation, it's still y equals 1 over x. It's still the solution for this thing, right? But now the domain is all values of x greater than 0. Okay? So it's only this branch over there. Okay. Similarly, if I were to tell you, solve this differential equation and let the curve go through 1 minus 1, then I'd be picking up this branch, and the domain would be all values of x less than 0. Okay? So the thing to take away from this is, like I said earlier, that when you talk about the solution of the differential equation, immediately, almost my knee-jerk reaction should be, what values of x is that valid for? What's the domain? It may not be all values of x. Okay? Solution, I think I have a better one. Another illustration here. Okay. Yeah. We'll see this over here. Let's do initial value problems. Okay? I talked about this, for Newton's law, namely this whole idea of solving a differential equation, and we know to get a unique solution, we have to put in subsidiary conditions, other types of data. For Newton's law, it's initial position and velocity. You saw for that beam problem that I did on Monday that there were it was a fourth order equation, and there were 4 conditions that had to be given. In general, the number of conditions specified is equal to the order of the equation. Okay? And let me kind of just put this down formally and illustrate it. Okay? And again, what's really nice about this is that you can get the same result from different approaches. Okay? I'm going to do something that the book doesn't have, and I'll tell you exactly that's going to happen. But this is called the initial value problem. Okay? A specific example of initial value problem is the one we did for Newton's law before, right? We had, remember, x double dot was a function of tx, x dot, y double dot, and we had to give initial conditions, in that case, initial position and velocity, to get a unique solution. Well, let's look at the context now of a more general setting. Okay? So, initial value problem for nth order equation, it doesn't have to be linear, is basically the following. Solve the nth derivative of y with respect to x, and that's that normal form. This is the same as that f of x, y, y prime, yn equals 0, but let's assume that we always solve for the highest derivative. So that's going to be some function of x, y, y prime, and obviously y and minus first derivative. Okay? Okay? And again, we're not going to prove existence theorems here. That's more for the graduate course. But kind of, it's not going to, what I can tell you, it's not going to be surprising. Okay? We saw that for first order equation, you just needed one initial position. Right? Second order, like Newton's law, you need initial position and velocity. Third order, what do you think? I need 3 pieces of data. The value of y, its first derivative, and its second derivative. And to solve the general nth order equation over here, I basically given y at some point x naught. X naught is some arbitrary point. It doesn't have to be 0. In mechanics problems, it's usually t, so it's 0. But it could be any point. Given x naught, y prime with x naught, y double prime with x naught. And where do you stop? N minus first derivative of x naught. Okay. So I've got this nth order differential equation, okay, right over there. And I want you to get a solution specifying that the curve goes from the point x naught, whatever this number is, has a specified slope, all the way to the n minus first So at this point x0, I'm telling you what the y is, I'm telling you what the slope is, all the way to n minus first derivative. How many conditions in total? N, right? N minus 1 derivatives and the function. Order of the equation is n, okay? So what happens is if you have an nth order differential equation, if it was a fifth order equation, for example, in order to get a unique solution, something you can have MATLAB compute, okay, you need 5 conditions, okay? Initial value problem is always giving those things at the same point. Maybe x naught equals 6 or something. It doesn't make a difference what it is, okay? Whether or not a solution exists is a whole other thing, okay? That's beyond the scope of the course, but assuming we're doing a physical problem, a model is, you know, representable, it's going to have a unique solution. Okay. What's the special case now? Let's do n equals 1. Let's kind of go back. N equals 1. If n equals 1, it basically reduces down to dy dx is a function of x and y, right? Where y at some point x0 is given. Okay? So what we're really saying over here when we solve the differential equation, okay, maybe there's a whole bunch of curves like we had before, and what we're specifying over here is it goes through the point x and y naught. Okay? Clearly for a first order equation, and we're going to do this actually in MATLAB next week, this specifies what's called the slope field, right? Since I have dy dx as a function of x and y, I can take the xy plane, break it up into a grid, right? And at any point, x equals 1, y equals 5, plug in, get the slope, And we'll have a program that I'll show you in MATLAB that calculates the slope at every point. Use these little arrows, kind of like a flow of what the solution looks like. So when you have a first order equation and you specify just y at x naught, it's saying find the curve that goes through a certain point, x naught, y naught. Okay? That's for the first order case. Okay? If it was a second order case, say n is equal to 2, then you have the second derivative of y with respect to x, n equal to 2, is a function of x, y, and y prime, right? And you have to give 2 pieces of data. Let's say, I don't know, y of x naught is equal to number a, and y prime of x naught is also given. Call that number d. Now, the difference between that and the original one is, again, I've got these solution fields. I can't do like I did before, you get the that little flow field. But again, this is a whole family of solutions. You saw that before, right? You have the general solution of that equation with all 2 arbitrary constants, and in order to graph it, you'd have to choose values for the c's. And you see curves all over the place. And what this is saying now is that the point to get the unique solution for the second order equation, I'm saying that it goes through this point, and I'm also specifying the slope, right? It goes through the point x equals a, y equals x naught, and y is equal to a. And I'm also specifying the slope at that point, right? dy dx at the point is what? The slope, okay? So for the first order equation, it's enough to just say the curve goes through a certain point. To get a unique solution for a second order equation, you have to specify not only the point that the curves go through, but the slope. And for the third order, you have to specify the second derivative, and I can't really draw that on a curve. Okay. Now, let me show you, okay, again from a numerical perspective, okay, you know, what's another way, why, you know, let's ask ourselves the question, you know, suppose I had a second order equation, okay? Why do I need 2 pieces of data to do that, okay? Well, let's try to solve this a different way. You're going to basically do a computer simulation. Okay? Everybody knows about Taylor series, right? Let's assume that the solution to the difference, so I'm basically doing the following. I have the second derivative of y with respect to x. Let me do a first order equation. Okay? Suppose I just dy dx is f of xy, okay, where y of x0 is given a, okay? That's the initial value, the simplest initial value problem, right? It's the first order differential equation, okay? And I tell it that it goes to a certain point, x naught a. Okay? According to, you know, basically we should be able to do that on a computer, right? Okay. Let's assume that we expand y in a Taylor series. Okay? Okay? Go back to your calculus, remember, y of x is equal to y. It's y of x naught, right? Plus y prime of x naught So, what's the first term in the Taylor series expansion? It's pi of x naught. You know that, right? That's A. That was given to you, right? So you can generate at least the first term in the Taylor series from the data, okay? Now, what about dy dx at x0? How are you going to get that? That's given to you by the differential equation. So get